All right, example 3.30. So here we're combining the quotient rule and the product rule. And so another one where we have a combo. And so h of x is the quotient of this numerator over this denominator, right? This numerator function over this denominator function. And this numerator function is a product of 2x cubed and k of x, right? So it has a product going on in the numerator. And so when we find h primed of x, let's first start, since the whole thing is a quotient, let's start by kind of laying out the quotient rule. So the quotient rule, remember, is basically f prime g minus g prime f all over g squared, right? Or low d high minus high d low all over low low. All right, so if this is f and this is g, then what I'll get is the derivative of this, right? The derivative of f, and that's where we have to now use the product rule, right? So the derivative of f, now we're going to do, let's call this m and this n, right? So then what we're going to do to find the derivative of f is that's going to be m prime n plus n prime m. Okay, so m prime, the prime of 2x cubed, is going to be 6x squared, and then we'll just multiply by k of x, plus now we're going to have the derivative of n, which is k prime of x, and then regular m, which is 2x cubed. Okay, so that whole thing is f prime. So now we just write down regular g, which is 3x plus 2. All right, and then minus, now we're going to do g prime times f, right? So g prime, the derivative of g is going to be just 3, right? So it's going to be 3 times f, and so f is this whole thing, so it's going to be 3 times 2x cubed k of x. All right, so we did the whole numerator. Now in the denominator we're just going to have g squared, which is 3x plus 2 quantity squared. Okay. All right, and this one is a big mess. There's certain times where simplifying is good practice and things like that, but in this case it's more about just understanding how it works. Like, I'm not as concerned that you know how to distribute and combine like terms, but since this is a mess already with a bunch of, we don't even have k of x in terms of value. So like if k of x was given, then we could actually do some simplifying, but yeah, this is kind of a big mess and not worth spending the time simplifying, so we'll leave it like that. All right. All right, here's a problem. This is one we had one like this on the assignment from the last class, and yeah, so determining where the function has a horizontal tangent, right? So when you see horizontal tangent, remember that means the tangent line is a horizontal line, of course, right? And that means that the slope of the tangent line is 0, right? And so basically what we want to do is we want to find, we know that the derivative of a function is at a certain point, is equal to the slope of the tangent line at that point, right? At x equals a. And so if we can find the derivative of f of x and figure out where the slope is 0, where f prime of x is 0, that will tell us where the tangent line has a horizontal, where the tangent line is horizontal. Okay, so we're going to first find the derivative. So power rule, 3x squared, power rule, negative 14x, right? And then power rule is that's going to be 8x, or excuse me, just 8. And then the derivative of 1 is just 0, so that goes away. So the derivative of a constant is 0. So, all right, and so now I'm going to set this equal to 0. Okay, and then from here we can use a quadratic formula. You can factor whatever works for you. Let's do the quadratic formula. We haven't used that in a while, or maybe not. We might not have ever used that in our class. So this is A, B, and C. And the quadratics formula is good if you have a leading coefficient greater than 1, and especially if you're not super comfortable with factoring complex quadratics like this. And that would be where we multiply A times C, and then we go from there. That would be the another alternative. So, to me, it's kind of either way. Like factoring is fine. I probably would prefer factoring, but the quadratic formula is nice because even sometimes this may not be factorable, whereas with the quadratic formula, it works every time, whether it's factorable or not. All right, so it's negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, right? So that's our formula. So it's going to be 14 plus or minus, and then I'm just going to, you can actually just plug this whole value in your calculator if you want to, but 14 squared is 196, and this would be negative 12 times 8 is negative 96. So 196 minus 96 is 100, and the square root of 100 is 10. So we're going to have plus or minus 10 here. Then on the bottom, we'll just have 6. And so we end up with 14 plus 10, which is 24 over 6. And so that's 4, right? I'll just write it out this way, 24 over 6. Or, and this is since we have a plus or minus, right? There's 2 of them. So 24 over 6. Or the other way is we do 14 minus 10, which is 4 over 6, right? And so 24 over 6 equals 4, and 4 over 6 is 2/3. And so those are the two x values for which we have a horizontal tangent line. So when x equals 4 and when x equals 2/3. All right. So now we could actually find those tangent lines by plugging in. If we actually plugged in the values into this original function, that would actually give us the outputs at those points. And of course, if those are the outputs at those points, that's the y value. For a horizontal line, the y is always the same. So you could just put y equals whatever that is. Okay. So if you wanted to, you could find f of 4, like not the derivative, because we know the derivative, if we plug in 4, we're going to get 0. But if you actually plug in 4 here, whatever that output that would be, if you set y equal to that, that's going to be your that's going to be the actual equation of your horizontal tangent line. And the same thing if you did y equals whatever f of 2/3 came out to be. All right, so they're not asking us for that, so this is fine, but just to give you a little heads up if that comes up.